Hey everybody, Lars here, coming to you today from the friendly confines of the cave. And I thought I would jump on, and I'm going to try and do this quick. I don't want to sit here for a half hour, 45 minutes. But I figured we'd review some of the stuff that's in the book and also in your slides about audio. If you remember back to week 6, we were talking about input and output and how you need to think out of the box, how input could be a mouse click, how input could be an infinite stream being read by your program, like we were dealing with output as a stream. Well, as output could be writing to your terminal window. Output could be graphics, could be a drawing, like we've been doing with STD Draw. But it could also be audio. It could also be music, and there's that optional part in your slides for week 7, I believe, when we do functions that talks about audio. And what usually happens is we're so busy getting down all the stuff we have to do with functions, and you're learning Java for the first time, and you're learning some computer science concepts for the first time, that we sometimes skip over the fun stuff. And when I say fun, if you're in my lecture, you know I always do this. I use the analogy of a musical instrument, which is why this is apropos. You need to practice. Okay? You need to practice and practice and practice because you're learning a computer language to do what? Solve problems. Eventually, you want to solve problems and do fun stuff. Right now, you're learning the basics. We're using toy programs that aren't really doing a whole lot. So sometimes it gets lost that, hey, we're doing this for a reason. You learn piano. You learn how to play guitar. You're doing it so you can play songs. You're doing it so you can play music eventually. But at first, while you're learning your scales and you're working through all of the early stuff, it doesn't seem like that, right? But you learn the early stuff, you practice, you practice, you practice, and all of a sudden that becomes easy, and then you can start playing songs. Okay? And then creating music becomes easier. Well, it's the same thing when you're starting with computer science and you're learning a language. You practice, you learn the basics, and you practice and you practice. And then all of a sudden that stuff becomes easy. I know how to grab an array. I know how to make a two-dimensional array. I know how to use functions. I know how to make different calls. Plus, you're going to get experience solving different kinds of problems. So when new problems come down the line, you're going to be like, oh, okay, I've done something like that before. Let's set up this. Practice, practice, practice. And then on the computer science side of things, your songs are solving problems. Okay, that's your songbook is problems. That's what I say about having large lists of problems. Is that's what you want to do with your computer science / computer programming skill is solve problems. That's the reason you're learning all of this stuff. So when you start working on actual problems, you're like, oh, okay, now this is fun. Now this is what I'm really doing this for. So I thought I would just jump on. No, I don't want that timing thing. And I'm going to leave it here. I'm not going to go full screen. And that we could look at the case study for digital audio, okay? Because this is actually fun. The book that we're using provides a Java library module called stdaudio, okay, which allows you to do things with audio. So if you read the slides and you take a look at this, and you don't have to be a musician, and I'm going to go over this, fairly quickly, but at the end of the day, music is math because sound is vibrations in the air that gets picked up by your ear. Believe me, they go into the science in the next slide. We're not going to do all that. Okay? And concert A, which is above middle C, is 440 hertz, which means that wave goes up and down 440 times per second. And when that kind of vibration or oscillation is detected by the ear, it sounds like A. And in Western music, you have the 12 tones going from A to the next A, which is called an octave. And you go, as you can see, it's all listed right there. A, and then A sharp or B flat, B, C, all the way down the line. And you can see the different frequencies for the different tones that you can produce. Okay? And they go up in a regular fashion. You're going to see what that is in a second. And we're going to call that pitch. Okay? Pitch is just how far are you away from A in this instance. Okay? You can see the waveforms over here. It's just a sine wave. Okay? And you're going to see we're going to use that. So that's all music is at the end of the day. It's a tone, and it's a tone that's defined by a certain frequency. And remember, frequency is how many times that wave goes up and down in a certain amount of time. The size of the wave, how big it is amplitude. That's your volume. Okay? And then your X is your time limit. And you're going to see that's neatly defined here too. So we're just going to be interested in finding the Y's. So it gets into the science. I'm going to leave that for you. You can go to the Wikipedia page and learn how your eardrum works and all of that fun stuff. And it's interesting. It's good to do. I don't want to, poo-poo it. It's just time is limited, so I'm not going to go through that. Now, where it gets interesting is we're using Java and we're doing Java coding. How do we represent sound? Because sound in the natural world is an analog process. It's something that's natural that we have to represent digitally in order to work with it with computer programming. So the way we do that is we try to mimic that wave. We try to find a way to represent the wave that is going on in the real world when we do our sound. And the way we do that is we can define the wave with our mathematics, but we want to know where it is at certain places in time. So what do? We go look. Okay, and when we go look at where that wave is at a certain period in time, that's called a sample. You've probably heard that before. And in order to make sure you really have a good representation of that wave, you want to get as many samples as possible. Okay, and as you can see there, you see that table. It shows you what different waves look like depending on how many samples you take. CD, compact disc, standard audio, to get that the way to reproduce sound, the way you want to reproduce sound at a high level, you actually want to take 44,100 samples per second to make sure you really have a solid definition of that wave. Okay? So in 1 second, you're going to create 44,100 values. All right? Because what are we doing? That's a sine wave. Okay? The x-axis here is time. So at 1, this is 0, this is 1. In here we have 44,100 samples. It would actually be here. It would actually be 1 second, 1 period. Okay, because that's what you're doing 400. Well, actually, no, that's not even true. Because you're doing that 440 times per second. Because that's A. So if you sample that, you're going to sample 44,100 times per second to make sure you get a good representation of whatever the wave is. The wave could be 440 hertz, it could be 880 hertz, it could be whatever. But that's how many times you want to take a look at that. And you're saying, like, well, how do I take a look at it? You use the sine formula. You know what x is because that's time, okay? To get the y, you use the sine formula with your x. Okay, it's not that crazy. The good thing about what we have here is we have the stdaudio library, and what that does is it not only allows you to play WAV files, and you guys are probably familiar with WAV files. You can also give this module an array of doubles, and it plays the tone for you. So you can create an array of 44,100 values, okay, of what a sine wave looks like for A, give it to that library, and that library plays the tone for you. That's the software we're going to play around with right now, okay? So now it shows you a little bit of code. I'm going to tell you right now at the outset, the code in these slides is a little bit different than the code in the book. In the book, in chapter 1.5, they have a small section on audio, all right, that goes from 155 to 159. Then, and we're going to talk about this too, they pick it up again in 2.1, defining functions, when they talk about the superposition of sound waves and putting sound waves together. We're going to do that too. And then that starts at 211 and only goes to 215. So it's only really about 8 pages of text in the book. But if you read the book, you'll see they do something a little different. When we get there, I'll show it to you. Right here, as far as this hello world, let's go look at some real code. I brought a bunch of this code in here. So what we have here is a piece of code called play that note. And what it does is you give it the hertz, how many times that frequency is. Okay, A is 440, and that's what we're going to use at first. And then the duration in seconds. So if I run this program and I give it 441, it should play concert A for 1 second. And how it does it is this. You can see down here I'm with my main. All right. I grab a variable from the command line called HZ for hertz. All right, that's the frequency. And then the second one, I grab the duration. All right, and that's a double as well. So you can do half a second, quarter second, other things like that. And that is going to be how long I want the tone to play. Then I set up an array. It's just a regular array of doubles. All right, and I call a function called tone, static function called tone. Tone is up here. What does tone do? Tone creates an array. The first thing it does is it takes n, okay? It creates a variable called n, and what does it do? It multiplies the duration by 44,100, because that's the samples we want, and it makes it an integer, okay? So that is the total amount of actual samples you're going to take. Because if you do it for 2 seconds, then what? You want to do it for 88,200, right? So that's going to be the amount of samples you're going to take. Then you create an array called A, and then you jump into a for loop. And this is a pretty big for loop because it goes till n, right? So if you do 1 second, that loop is going to loop 44,100 times. And what do? For every time interval, okay, you're going to run the sine function on it. And you're going to run the sine function on it with, read the book and read the slides, 2 pi is the period for these frequency waves and these sine waves. So when we do that, and we do it with our frequency, we're going to get the y value, and we're going to create our array. And then when we're done going through that loop, we're going to return A. So what we're going to return is an array with all of the y values for that sine wave that represents that frequency. Okay? So that's what you're doing when you go to that tone function. You're creating a big array of doubles that represents the y values in that graph. All right? And then all you're going to do when it returns is send it to stdaudio.play. And it will play. I don't want to say play that tune. I'm fighting the urge, but that's what it's going to do. It's going to play that tune. So if we come down here, I'm going to say Java, play that note. And let's say 40, and I'm going to play it for 1 second. Okay? And there you go. Now, what you learn, and I always say this to people, is that music is math, is that if you double the frequency, it's the same tone, but an octave higher. So if we do 880, that's A, but it's an octave higher. We can also knock it in half, and that's A, an octave lower. Okay? Now, you can tell tonally, they all sound kind of familiar. If we just go grab something random, you'll see it doesn't really sound the same as the other ones we heard before. Because it's not the same note, if you will. It's not an A. Okay? So now, very simply, and it seems like a lot of work to get to this point, but we can play any frequency of sound we want for any duration of time we want. And if you think about it, what is a song? Just changing all those different tones and playing them for different periods of time to create music at the end of the day. So what I did really quick is I jumped in, and this is just something I did, so it's not going to be in your book or your slides. And I said, all right, let me start at A and go up the scale and play the different tones. So all I did was jump in, and I created a loop that goes from 0 to 12. And what I did was I do the math for the pitch every time, which is just 2 to the power of pitch over 12, all right? Which jumps it by like 1.06 every time. And that's how pitch works. If you want to get 3 notes away from A, then it's, 3 over 12, power of 2. So if you look at this code, you'll see that then I say play that note tone, but that creates my array. So I want to save the array. I want to make sure I capture what comes back from that function. And then I send it to stdaudio. Okay? So when I do this, when I call this play with audio, I don't think I take anything from the command line. And it'll go right up the scale. Now, you might be freaking out because you're saying, like, where's the output lines in that program? They're not there. That's an old version that I had compiled before, and I had print lines in there to show me my values if it went up the line. You can add them back very easily by just printing out I, P, different things along those lines. So that's the basics. It sounds like a lot, but we're now at a point where if we give the program a pitch, okay, 0 would be 440, 1 would be 440, and then you would go up from there. And a duration, now we can play songs, right? So that's what this program here does. It's called Play That Tune. Now it uses Play That Note. So if you want to play around, make sure you have Play That Note installed too. And Play That Tune reads from an input stream, okay? And what does it read? First it reads the pitch, then it reads the duration, okay? Remember, pitch is right here. It's how far away you are from A. So A, in computer science, starts counting at 0. A is 0, so a B would be, the pitch would be 2. A C would be 3. And as you can see, they do the math and actually compute the frequency of that different tone, okay? So now we're at a point where if you just give it the pitch and the duration, what does it do? This also messes around, and this is also not in the book, and adds tempo. So if we wanted to, we can play it faster or play it slower. I'll show you that as we go through and do it. So we take pitch, which could be 1 through 11, frankly, and then duration, how long you want to play that. And then we multiply the duration by the tempo. Tempo is something that we're going to give at the command line. And it could be, one, it could be a half, it could be 1, it could be 2. I think 1 is normal if we want to play things quicker or slower, okay? So now hertz, we grab the hertz by taking 440, concert A, and then we do the math. And as you can see here, the power of 2 to the pitch over 12 is how we calculate where that actual frequency is. Then what are we going to do? Just like we did in the other program, we're going to call tone. We're going to call it with our new hertz that we just figured out and the duration, and then send it to play. And then it will be played. And as you can see, this is all in a while loop. So as long as it's not empty, we're good. All right? And as an example for this, I have a small file here I call Small Elise, and it plays the beginning of Fur Elise, which is Beethoven. I forget the opus, whatever. And you're going to see I have a 7 and then 0.125 for the duration. Okay? So whatever that is, 1/8 of a second. And then 6, 7, 6, 7. So do. And you'll see I just played this small one, but we're going to be able to play bigger ones in a minute. So I go to play that tune. Remember, I'm using a Windows box here. So what I want to do is I want to do a cat, or I want to take this and throw it to the input and then pipe it to my Java. So I'm going to Java play that tune. And I want to give it a tempo, or it's going to yell at me because it's taking input from the command line. So I think I'm just going to give it 1.0 for the tempo. And then what it's going to do for the input read is it's going to read Small Elise. So it's going to read all of those values from the small Elise file. And when I do this, okay, if I want to slow that down, how do I slow the tempo? I make the tempo lower. No, that makes the tempo faster. If I want to make the tempo, I don't know that makes sense. There we go. Okay, so it read small Elise, and created, obviously, music, something most of you probably recognize or have heard before. Okay, so now, using just arrays full of doubles, we're sending it to the audio file, and we're playing tones. Then play that tune. If we know our notes and we know how to put songs together, now we can tell it the pitch and the duration, and send it to play that tune, and we can play music. Okay? And don't forget along the way that as we're using these things, we're using functions, and we're compartmentalizing our code. So when I do a tone and create that array, I use the tone function. And then when I come here with play audio, I use the tone function here. So I'm reading it from a library. Modularization, compartmentalization. Okay? Only this is code that's actually doing something, so it's more of a system, which is why I wanted to do this video, and I like this example. Right here, we're using what we know about pitch, and we're creating our different frequencies on the fly, and then we're sending them to tone to create those arrays, and then we're playing them. Okay? When we play them, it's only the one note. They're all separate. They're all separate arrays. As you can see, the array creation and the playing of the array are all here in the while loop. So every time it goes through the loop, it creates and plays a new array. All right? So now, the very last thing we're going to talk about, and I don't want it to get too confusing, is play that tune deluxe. That this exists in the slides. Okay, if we start reading, that creates noise, average, chords. This code right here is the same as play that tune deluxe, but there's one difference, and I want to point it out to you guys because it confused me at the beginning, and I'm guessing it's going to confuse you too. This code at the top renames this function and calls it average, AVG, because that's what's used here in the slides. All right? Here in the slides, something different than the book is going on, and they're showing you how to average an array and create a new array with equal parts of two different arrays, okay? And then they do something called play that chord, and then they put two notes together, which makes no sense because chords are three notes, but I digress, and uses average when it discusses harmonics, which we're going to discuss in 2 seconds, okay? So it uses the average code it's been using. In the book, you get what's called weighted sums, and my guess is when these slides were done, they said weighted sums is too crazy, let's just make it an average. And I don't think weighted sums are that crazy, so I'm going to talk about the weighted sums. If you come to the code, and I got the code from the book site, Java code, if you come down here where they talk about functions, play that tune deluxe is right here. introcs.cs.princeton.edu java/code. It's the code that goes along with the Sedgwick book that you have. Okay? It's right there. Play that tune deluxe. Anyway, you'll see in the beginning in the comments, it has the URLs for all of these different music files. So you can download these, like I got the tiny little for Elise with these things. Well, if you come here, you get the big, long, regular version. As you can see, I grabbed the entertainer, and we're going to play that. Do I make that short? No, it's the regular long size. And we're going to play the entertainer. If you haven't seen The Sting, go see it. 1973. Paul Newman, Robert Redford. Great movie. All right, I digress. So now, play that tune deluxe has 4 functions. Okay? Well, one is the main function. And it's going to read the numbers from entertainer that are going to give it the pitch and the duration. Pitch, duration, pitch, duration. Okay? So what does it do? Well, input isn't empty. It reads pitch. It reads duration. and then it sends it to note. So far, this is what we've just been doing. So let's come up here and look at note. Note is a little more complicated than it was in the past. By using the pitch, it calculates the frequency, okay, by doing what we've been doing, taking the second power to the pitch divided by 12 and multiplying that by our 440 to go up the line. But it's doing something different here. Look what it's doing. It's going in, it's getting 3 different arrays. It's getting an array for the tone you're asking for. For our example, let's say it's 440A. But here, it's also doing 880, and it's also doing 220. And what, if you read in the book, or if you know a little bit about music, you'll know that sometimes when you play music, piano, guitar, when you sound a note, there are also going to be other sounds around that are called harmonics. And those harmonics are when that note sounds in another octave, but not as loud as the tone that you play. So if you play an A, you're also going to get the A's from other octaves, but not as loud. And that's what this is doing. It's creating an array for the tone. It's creating an array for the tone up an octave, which is why it's calling it high. And it's creating a tone for below, all right? And then it's going to create one array called H. That's the sum, all right? Actually, what's going on here is the H stands for harmonics, and it's taking high and low, and this is where you get the weighted sum. And 0.5 each, so they're equal. It's creating a sum of the 2 arrays. And you're like, sum? Where's sum? Boom, 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 right up here. This is the sum function. And what it does is it reads 2 arrays, and it sends you back their sum, but not really their sum. It doesn't add them and send that back. It's a weighted sum. So if you send 2 arrays and you say, I want 75% of this and 25% of this, that's what it does. So that's why we have the A weight is 50, the B weight is 50. So in this case, you're getting an average, all right? So if you're using 0.5 all the time, technically you're doing an average, which is why I think the slides got dumbed down a little bit. But it's not, it's not crazy to understand this. So what am I going to do? I'm sending it my high A, my 880, which is the high harmonic. I'm sending it my low A, which is 220, which is the low harmonic, and I'm getting the average. All right? And then I'm creating that array, which is just the Y values. All right? And I'm going to return that as my sum, my weighted sum, or in this case, my average, because they all have the same weight. So that's all this little function here does, is it takes 2 arrays and it creates another. Here, I'm pretty sure for the first time, you see something called an assertion. Remember when you did your pseudocode and you had preconditions? And you said, hey, what am I preconditioned? I'm not going to check for it in the code, but I ain't taking anything less. That's what this does. Think of assert as a precondition. The 2 arrays, in order to do this properly, have to be the same length. So here I'm checking that. But I'm using something called an assertion. A little bit beyond the scope. We'll learn about them later. All right? So this does a sum of the arrays. It takes 2 arrays. You can weight them however you want. Here we do them both the same. It sends back a sum. So that's actually pretty cool. So here we get the sum of the harmonics, and then we do sum again with your code, your regular tone, and your harmonics. And you weigh them evenly too, which is, I would do the regular tone a little higher than that, but that's opinion. I'm taking half of the tone I want, the 440, and the other half is the mix of the harmonics. Okay? And put that together, and that's my array that's going to come back from note. So here's the array that's going to come back from note. In this case, and this is why it's deluxe, it's mixing the harmonics and the regular note and coming together. Okay? And when we play it, you're going to see the difference because we're going to play small Elise. All right? The only other thing that's different here is the actual tone function. Okay? Because note calls tone to get the tone. And here tone is using the sample rate, which is in the audio. Guess what that sample rate is? It's 44,100 because that's the standard CD sample rate. So it's using that. When you see sample rate, don't worry about it. We're just not hard coding the 44-100 anymore. That's what the sample rate is. Other than that, it's doing everything same way we did it in the past. Okay? It's creating that array of 44,100 items per second. That is the Y values in the wave that represents the sound. Okay? Only here we have sum, which gives me a weighted sum of two different arrays, so we can add the harmonics. And here note creates the harmonic arrays, mixes them together, and then mixes the harmonics with the regular note. Okay? It returns that here. Creates the array and then sends it to stdaudio. So here, what did I do? I played that with a 2. So I'm going to play Small Elise with Play That Tune. I should do it with 1 because I think that's how fast it's going to go with Play That Tune Deluxe. So now, what if I want to send it to Play That Tune Deluxe? And that doesn't take a tempo, so I think this is all I have to do. Listen. Sounds more like an organ, right? This is the old one. That's the new one. That's Play That Tune Deluxe. So that's the difference you get when you add the harmonics. It's richer. It sounds better. It sounds more natural to our ears because there's a lot of things going on with frequencies when we play notes. If you want to just be cold and hard, that's 440, right? But if you want to do it like you're reproducing music like you would with an instrument and what we actually hear in the world, that sounds a little bit like an organ to me, which makes sense because think about it, all the organs are digital now, right? So that is Play That Tune Deluxe. What you're going to learn is if you go to the top, there's a whole bunch of songs here. Now, some of them are getting a little bit old. Stairway, I don't know how much you guys know about Zeppelin anymore, but that's from the 70s. Entertainer was from the 70s. These are old dudes. There's some Freebird. Oh my lordy Lou is Leonard Skinner, and that's from the 70s. Für Elise is Beethoven, but at least it's classical, and you should know that. I grabbed the Entertainer, okay? And what you can do is, I'm going to come here. And as you can see, I'm going to cat Entertainer, and I'm going to send it to Play That Tune Deluxe. Control-C to stop it in the middle if you want to stop it in the middle. I also have a regular release. I downloaded some others, and that works. My advice to you, if you have a little bit of free time, and I didn't drop this before the second quiz, and I didn't drop this before the assignment because I wanted you working on that stuff. But now that that's over, if you have 15 minutes, half hour, take a look at this code. Take a look at what it's doing with the functions that it calls and the way it deals with arrays and the way it manipulates arrays and does the sum, the weighted sum or the average of the arrays. And play around with this stuff. Go look at the different songs and change the pitch, change the tones, make it faster, make it slower. This is how you learn. And if you have cool stuff to do, like playing music is more fun than just doing an array and filling an array with the cubes of numbers and different things like that. At least here, you can create some music and try some different things. And if you have some experience with music, well, then you can go nuts and realize that this is the very, very beginning of playing music back. Think about the music files. Those music files are long and large because they're storing the representations of real analog sound waves that need to be examined and played back. So to our ear, it sounds like the actual sound waves that create those effects in our ears. Okay? Probably went longer than I wanted to, but I did want you to see this. I did want you to know that at the book site, a lot of this code is available, and it will give you the URLs to go get the data. Again, in that chapter, the second chapter, I don't know if the Gaussian stuff does it later on in the slides, but in that chapter, you get the IFS program with all of the different Sierpinski's triangle, the choral, different things like that. Those data files are online. If you go grab the IFS from the Java code, you can grab those data files and you can learn about the random patterns with the different formulas that are so random at the end of the day. You do the leaf, and you can do the coral and the trees and all of that stuff. And Sierpinski's triangle, which now that week 8's taken us into recursion, I think Sierpinski's triangle might be rearing its ugly head again. All right? So that's it for now. Like I say all the time, play around with this stuff. All right? This I think you get a kick out of, especially if you like music, because you're actually doing something that's real and you can manipulate it and play with it, and it's like solving a puzzle. All right? Then I'm going to get out of there. If you got one of my sections, I'll see you in class. If not, I'll see you around when we do the next video. All right? Talk to you later. Bye.